This is a demonstration of elements of our model-based systems engineering suite, specifically Teams Designer, Teams KG, and Teams RDS. This introduction to Teams Designer highlights how our modeling environment enables scalable, model-based systems engineering using a hierarchical graph architecture. Teams Designer supports the development of highly structured, hierarchical system models that scale from full system views down to individual components and failure modes. The graph-based structure allows engineers to navigate complexity without losing traceability. On the left side of the screen, you see the system hierarchy for a sample vehicle platform, a 2001 Lincoln LS. At the top level, the system is organized into major subsystems such as body and paint, chassis, driveline, steering, suspension, electrical, and powertrain. This hierarchical structure allows users to move seamlessly from enterprise-level architecture down to subsystem and component detail. In addition to structure, the hierarchy highlights associated tests and failure effects. For example, within the chassis system, we can view brake system failures, inspections, and related diagnostics, all directly linked to the relevant components, allowing for multi-level decomposition and failure modeling. Traversing into the brake system under the chassis, we see further decomposition into disc brakes, anti-lock brake system, brake booster vacuum hose, and supporting modules. Each subsystem can be expanded to reveal control modules and associated failure modes. For example, within the ABS control module, we can define specific failure effects such as ECU faults, voltage anomalies, or other model degradations. Every failure mode is directly linked to relevant tests, enabling fault-to-validation procedure, functional decomposition, failure mode definition, test traceability, and impact analysis, all within a unified model. Let's examine fault management capabilities, specifically automated fault tree and cut set analysis. If we select an ABS failure effect, we can automatically generate a cut set report and a graphical fault tree. With the system in its default configuration, the analysis identifies all single-point failures that can independently lead to ABS failure. Because no redundancy is modeled in this configuration, the report shows only single failure cut sets. The graphical fault tree provides an intuitive visualization. Each individual failure path propagates logically to the ABS failure effect. Engineers can immediately understand causal structure without manually constructing the tree. This capability enables rapid safety assessment, design and optimization studies, redundancy evaluation and configuration comparison, as well as configuration and retrofit analysis. One of the powerful aspects of the platform is configuration analysis. For example, we can reconfigure the system to include traction control. With this configuration enabled, faults within the traction control module are now allowed to propagate into the ABS module. Regenerating the analysis immediately shows additional failure paths. If we further enable Stability Assist, the model automatically expands the failure space again. The cut sets increase accordingly, and the fault tree updates in real time. This enables engineering teams to compare design variants, evaluate feature additions, perform retrofit impact analysis, and quantify reliability implications, all without rebuilding the model. Next, we demonstrate integration with the Teams Knowledge Graph application. This capability augments the modeling process by identifying potential failure modes, effects, and supporting technical content. For example, consider a power steering pump. If failure modes have not yet been defined in the model, the knowledge graph can surface relevant failure behaviors and observable symptoms. We can then add a generalized pump failure, define observable symptoms such as low output flow, attach test document specifications, and threshold criteria. An example of this is encoding flow rate specifications directly into the model and link corrective actions such as pump replacement when values fall outside tolerance. This ensures that technical data is captured, test procedures are linked to symptoms, failure logic remains consistent, and engineering knowledge becomes reusable. Future enhancements will allow automated population of failure modes and tests directly from the knowledge graph, accelerating model development. Finally, we demonstrate RDS, our model-driven guided diagnosis and troubleshooting system. RDS operationalizes the engineering model for use by technicians in the field. In this example, The symptom selected is vehicle will not start. The reasoner immediately recommends required resources, adapts if tools are unavailable, prioritizes likely causes, and guides the user step by step. If a resource such as an ammeter is unavailable, the reasoning engine automatically adjusts the troubleshooting path. The technician is guided through structured diagnostic steps, complete with clear instructions, warnings and cautions, images and contextual enrichments. As tests are performed and results entered, the probabilistic reasoning engine updates likelihoods in real time. For example, if the headlight test fails, the system evaluates battery-related causes. If certain tests cannot be performed, the reasoner dynamically reroutes the logic. If components are marked as recently repaired or repair not needed, the reasoner updates the strategy accordingly. In this scenario, the system converges on battery replacement as the most probable root cause and guides the technician through the repair and reset steps. At the conclusion of the session, RDS automatically generates a structured case report that documents system configuration and revision, tests performed, outcomes, pass-fail or cannot perform status, repair actions taken, resource availability, and total diagnostic and repair time. This report creates a digital thread from design model to field action. Most importantly, the captured session data can be fed back into analytics pipelines to refine failure probabilities, improve diagnostic sequencing, identify documentation gaps, and enhance future model revisions. This closes the loop between engineering design and operational performance. In summary, our model-based systems engineering suite provides scalable hierarchical system modeling, integrated failure mode and test traceability, automated fault tree and cut set generation, configuration and retrofit analysis, knowledge-augmented model development, guided model-driven troubleshooting, and closed-loop operational feedback. The result is a unified digital engineering environment that spans design, analysis, validation, and field support, turning system models into operational decision assets.